Hello and welcome to today's lesson, which is sort of lesson 4, part 2. It will be a relatively short lesson again, because once we've done this lesson, the next lesson, and obviously the previous lesson, then we can start to answer the sorts of questions that they're going to throw at you. If we've only done one part, it's quite hard to give you any sort of challenging questions that will otherwise quite simple. So the work will be relatively short today, but very important nonetheless. So last lesson, you had to find out what these words meant. Atmospheric pressure is obviously the standard pressure of the atmosphere that we experience at roughly sea level. It's about 101 kilopascals. Pascal is obviously the unit of pressure. It's 1 Newton per meter squared. A closed system is a system where nothing can enter or exit it, which is important because it means the mass is constant, the number of molecules is constant. An open system is obviously the opposite, mass can enter and exit. PSI is an imperial unit of measurement, it stands for pounds per square inch. So again, it's a measure of pressure like Pascal, but imperial units. We're not really going to use it, but it's important you know what it is in case you're looking at old textbooks on the internet on an American site. Brownian motion is the erratic movement of particles suspended in a fluid. That means a liquid or a gas. And they obviously move randomly all over the place because they're constantly being bombarded by the particles in that fluid, by the gas or the liquid atoms or molecules. Really, although it's kind of obvious these days, it's really like revolutionary kind of discovery, because it really did kind of prove the existence of atoms. Einstein did a lot of work on this, and obviously he wouldn't have been working on something if it wasn't really, really important and worthwhile. Iso is a Greek prefix meaning the same, so isothermal, the same temperature. Okay, today's lesson is going to be on the pressure law. It's also known as Gay-Lussac's law, but you very rarely ever see this term. It's usually just known as the pressure law, or sometimes not even known as the pressure law. It's just known as a mathematical relationship, but it's worth knowing of these names. So 3 questions for you to think of. So pause the video now and think through these questions. Okay, so hopefully some of you recognised some of these ideas from GCSE. So deodorant can gets colder when you spray it. The pressure is decreasing, and as the pressure decreases, the temperature decreases. Why is that? Well, it's sort of incorporates ideas from the next lesson as well. But in order for you to take that gas from a very compressed state and expand it, it needs energy to expand. And where does that energy come from? It comes from the surroundings. It comes from your hand. It comes from the room. So if you had a deodorant can at an extremely cold temperature, it's not going to work because there's not enough energy in the surroundings to cause it to expand and leave the nozzle. A bicycle pump getting warm and use it is the opposite. We are compressing the gas. We are decreasing the volume. We are increasing the pressure. And that means the temperature is going to go up. We are supplying energy to it to force it all into a small space. And so effectively the energy from our arm as we pump the bicycle pump is going into the kinetic energy, and therefore the temperature of the gas particles. And then hopefully, of course, you will know that increasing temperature increases the pressure in a gas. Specifically, pressure is directly proportional to temperature. It will be a straight line through the origin. 2 questions for you though. 1, what units do we need to work in for it to be a directly proportional relationship? And 2, what needs to be kept constant? So hopefully it's fairly obvious what has to be kept constant. The volume has to be kept constant for this to be true. And again, it should be obvious, hopefully, that it has to be in Kelvin, because then we actually have an absolute scale. So absolute scale, it starts at 0 and increases. Pressure obviously starts at 0 and increases. If you measure in degrees Celsius, you'll find that it is a straight line. It's a y equals mx plus c relationship, but it has some intercept here. So the pressure at 0 degrees Celsius is obviously not going to be 0. And then if you extrapolate that line backwards to 0 pressure, then you get minus 273 degrees Celsius or 0 Kelvin. So today's lesson and also next lesson also gives us two ways of finding absolute zero. And one of the things we would do at school is you will work out what absolute zero is using one of these experiments. And you can get pretty close values. I've had a number of students get within a couple of degrees of absolute zero when they've been very, very careful to get precise results and accurate results. And that's truly astounding, really. You can use very, very cheap equipment to find this amazing kind of constant nature. So mathematically, of course, pressure over temperature is a constant, or pressure is some constant times temperature, which gives us this relationship here. Okay, so questions like this are very common, fairly simple on their own. So pause the video now and work through this question. Okay, so when I first did this, I just chucked in some numbers on a calculator and got this. What mistake have I made? Because this answer is incorrect. So hopefully you realized that I was very silly and I just chucked in 100 degrees Celsius as my initial temperature and 20 degrees Celsius as my final temperature, which of course is wrong. I must change to Kelvin to make this work. Like on these graphs here, it has to be in Kelvin so that it's directly proportional. So when I do that in Kelvin, 100 degrees Celsius, 373, 20 degrees Celsius is 293. I actually get the final pressure as 80 kilopascals. So importantly, it doesn't matter that you work in kilopascals because it's a ratio and so the kilobits will cancel, but it's not a ratio with temperatures because to convert from Celsius to Kelvin, we are adding a fixed amount. We're adding on 273. So we can't do a simple ratio because the adding will not cancel in a simple ratio. If you don't believe me or you're not entirely sure what I mean, write it out. So write out for the temperature, put in brackets 100 plus 273, and the final temperature put in brackets 20 plus 273, and you'll see what I mean. You'll see that obviously it doesn't cancel as if we were just multiplying by this fixed factor of 1,000. So there's not too much else for today's lesson, but it's worth showing you these, which are called phase diagrams. We're going to look at two. The first one is for water. And what are they showing you? So the y-axis is pressure, the x-axis is temperature, and they show you what the state of a substance is at various temperatures and pressures. So this is for water. So at 1 atmosphere, which is what we're at on Earth, it's a solid, obviously, until 0 degrees Celsius. Then it's a liquid until 100 degrees Celsius, and then it boils above that. But if we increase the pressure, what happens? Well, actually, it becomes a liquid earlier. The temperature decreases at the melting point, and the boiling point changes as well. The boiling point increases as well. So water is very interesting because a solid is actually less dense than a liquid because of the way that the water molecules arrange in a very regular structure as a solid. They actually end up with little gaps in between them compared to a liquid. So actually increasing the pressure does melt it. So you can see that here, if we pick a fixed temperature here and just increase the pressure, we melt it because we're squashing it together, making them all go closer together, and therefore it becomes a liquid. Most substances do not do this. Water is possibly the only one or one of the very few that does this. And this is really interesting because it means water does a lot of things that other substances don't do. So, for example, if water didn't do this, then ice wouldn't float on water. And the oceans would be completely solid, because when the water froze, ice would sink to the bottom of the ocean, and then it would freeze from the bottom up, which means that probably life on Earth wouldn't exist. However, because ice floats, because it's less dense than water, the ice sits on top of the water, and it actually acts as an insulator, keeping the water underneath liquid, which means that life could exist in the oceans even when it's frozen over. Now, there's two other points on this graph that are worth highlighting. There's this triple point here. This is a very special point at this temperature, where you can actually exist at all three phases at once. All right, so it can be a solid, a liquid, or a gas at the same temperature and pressure. Just like at 100 degrees Celsius, it can be a liquid or a gas, or 0 degrees Celsius, it can be a solid or a liquid. At this point, it can be all three, and that's called the triple point. Finally, there is this point up here called the critical point, where above this temperature, above this pressure, it becomes this thing called a supercritical fluid. I would recommend a little bit of reading on this, because they're really interesting, they're really weird. It basically is a point where the boundary of what is a liquid and what is a gas doesn't really exist anymore. Things are both liquids and gases at the same time, and they do some very weird things. I believe Jupiter's atmosphere is thought to be full of supercritical fluid at various depths because of the very, very high pressures. So it might be worth a quick Google. I'll just quickly show you the phase diagram for carbon dioxide, because it's quite interesting. At 5 atmospheres, we get this triple point here. At 1 atmosphere, we're below this triple point. So if I get a lump of carbon dioxide, it will either be a gas. If I cool it down, it will be a solid, and it will sublimate from a solid to a gas. There's no liquid phase. The only way I can get a liquid is to massively increase the pressure. So it shows you a very nice contrast to water, because water obviously doesn't do this at our pressure. If you decrease the pressure a huge amount, then it will do this. It will sublimate, as most substances will, but not out at our pressure. Part 2, quick look at determining the pressure law experimentally. 2 methods that are pretty similar, to be honest, but a couple of subtleties. So the method is obviously extremely simple. You increase the temperature, you measure the pressure, you do this 10 times or so, you plot a graph, you should get a straight line. Pressure is proportional to temperature, as long as we're working in Kelvin. However, it's worth showing you that we can do this in different ways. We can do this with a simple pressure meter, where you just literally read off a scale, or we can use this thing called a manometer, which is a more old-fashioned pressure gauge. I think biologists might use these in certain experiments, and they're relatively simple. What happens is you have a U-shape bit of glass tubing, which usually has water in, or maybe mercury, depending on exactly what the pressure is, if it's higher. As the pressure increases, the pressure causes the gas to expand and push this water up. And then on this side here, there'll be some markings. There'll be a scale, 0, 1, 2, etc. And the higher up it goes, the higher pressure it is. If this pressure is equal to the pressure outside, obviously these water levels will be equal. If this pressure is higher than outside, then this side will be lower than the right-hand side. And if the atmospheric pressure is higher than inside, then the left-hand side will be higher, the right-hand side will be lower. What else is interesting here? Well, it says dry air inside. What does dry air mean? Well, it means that basically there's no water in the air. So we've managed to remove all the water, we've removed all the humidity. Why is that important? Well, we don't want any impurities, effectively. We don't want any other variables in here. So we don't want any water vapor that's going to behave differently when we heat it up. So we only want air. We only want oxygen, nitrogen, a token amount of carbon dioxide or argon. So that's what that dry means. It basically means pure air. What else? Well, we can use a Bunsen burner or we can use a water bath. What are the advantages and disadvantages of both of them? Well, a Bunsen burner is faster. But does faster mean good? Well, probably not, because as we heat up the water obviously takes time to heat up, but it also takes time to heat the metal ball up, and it takes time to heat the air up inside. So if we heat the water too fast, the air inside might not actually be the same temperature as the water outside, and we're likely to have an error there. So we actually want to increase the temperature quite slowly so that the air inside has time to heat up. So probably Bunsen burner is a bad idea. We probably want to use a water bath. And then finally, is this diagram on the left actually that good? Well, maybe not, because all of this section here isn't in the water. So all of this section here isn't being heated, but yet it's still contributing to the pressure. So you really need to make sure as much as possible is submerged in the water, so we're heating it all up. Now, it's only going to be a small effect because the volume of this little bit here is quite small compared to the volume of the copper ball, but it's still significant. It still could be 1%, 2%, and we're always trying to reduce errors. So there's a slightly longer method here, but it really is quite a simple method. This equation here, don't worry too much about now. We'll look at that in 2 lessons' time. So there's not too much work for this lesson. I'll probably put a short quiz up, but I would like you to, like last lesson, find out what these words mean, because they are really useful for your understanding. If you start seeing these in work or textbooks, you don't know what they mean, it can really throw you off. And then also think about, can you actually achieve these changes in reality? Goodbye. I'll see you next lesson.